Okay, so let's see what is the meaning of a sequence of vector being linearly dependent or being linearly independent. So as the definition suggests here, that if we have a sequence of vector v1 v2 till vk from a vector space, and we have already seen the definition of vector space. So if we have this sequence of vector and this sequence of vector is from some vector space V, then it is said to be linearly dependent if there exist scalars, k scalars basically, a1 a2 till ak, not all 0, such that this expression is satisfied. Okay, so a1 into v1 plus a2 into v2 plus till ak into vk should be equals to 0. So this is a 0 vector here. Okay, so you look at this particular expression here, because right now we don't know. When we will be having some problem or some numerical, we will be not knowing that a1 a2 and all the ak's are all zeros or not. So I'll be basically interested in finding out these solutions for these particular scalars. Okay, so let's say, so this is a condition for linearly dependent vectors. What if there exists no such solution other than all zeros, other than a1 a2 and all ak's equals to 0? If this is the only solution that exists, then we say that this sequence of vector is linearly independent. Okay, so linearly independent vectors are very important in linear algebra. They play a crucial role in representing the vector spaces. Okay, so we'll take an example and we'll see how to proceed to find these values. Okay, so let's say that we have two vectors here. v1 is equals to 1 and 1, and v2 equals to -3 and 2. Okay, so we have these two vectors and we want to find whether these two vectors are linearly independent or not. Okay, so what we'll do, we'll just use this expression here and I'll write them as a1 into v1 plus a2 into v2 equals to 0. So basically our motivation is to find these constants or these scalars. So there are basically two methods. This will create a system of equation here. So like we can write it like this: a1 into this vector plus a2 into this vector equals to 0. Okay, this can be written as in a matrix format. Right? You can use a lot of techniques here to solve this particular equation. One is Gauss elimination method, and second is your usual, like what we were doing in our basic classes. Okay, so what we can do, we can find out two equations and we can do it via substitution method, right? Well, we'll try this Gauss elimination method, and then I'll tell you one more technique that can be used to solve such kind of specific examples, and we'll be looking at this particular matrix. So basically we have this matrix 1 1 minus 3 and 2, and these are the variables, and we have this system of homogeneous equations. What we can do here, we will apply some operations here. Okay, so applying row operations, we'll try to make this 0 and this 1. Okay, so let's apply a row operation. R2 equals R2 minus R1, right? What we'll get? We'll get 1 minus 3 and 0. Okay, so R2 minus R1, and this will be minus will become positive, it will be 5. Since they are 0, nothing will change here. Okay, next thing we can do, R2 equals to 1 by 5 R2, right? And this will make this particular value at 2 to 1, and we'll apply another operation after this. We'll say R1 equals to R1 minus, or we'll sum it up, 3 R2. So this operation will make it 1, and after this place will be replaced by 1. Okay, what we'll do, we'll add this row with this row after multiplying this row with 3. Okay, so after that what will it become? It will become 1, this will become 0, this will become 0, this is already 1. Okay, what does this show? It shows that A1 equals to 0 and A2 equals to 0. So there is no other solution. Basically these are the solution. These solutions are the only solution that we have, that we are getting from this particular relation here. What does it mean? It means that all the AIs are 0, and this implies that our vector 1 1 and minus 3 2 are linearly independent. Okay,